This research paper, titled GeoSense, Evaluating Identification and Application of Geometric Principles in Multimodal Reasoning, focuses on assessing how well multimodal large language models, or MLLMs, handle geometry problem solving. Geometry problem solving involves understanding spatial relationships and using symbolic reasoning to solve problems based on visual diagrams. The authors, from Taobao and Tmall Group of Alibaba in Beijing, China, highlight that humans excel at this by accurately identifying geometric principles and then applying them adaptively in different contexts. The paper begins by noting that existing benchmarks for MLLMs often only check if the final answer is correct, without deeply evaluating the reasoning process. This leaves a gap in understanding how MLLMs identify and use geometric principles, such as definitions, theorems, and formulas. To address this, the researchers introduced GeoSense, the first comprehensive bilingual benchmark designed specifically for this purpose. GeoSense is structured around a 5-level hierarchical framework that covers geometric principles in both plane and solid geometry. This framework organizes principles from basic concepts, like the properties of shapes, up to more complex theorems. For instance, it includes things like the definition of a radius in a circle or the triangle angle sum theorem. The benchmark also features a carefully annotated dataset of 1,789 geometry problems, which are designed to test various aspects of reasoning. These problems are bilingual, meaning they're available in both English and another language, likely Chinese, to evaluate MLLMs across linguistic contexts. The evaluation strategy in GeoSense is innovative. It breaks down performance into 3 key metrics: GPI, which stands for Geometric Principles Identification, GPA, for Geometric Principles Application, and ACC, for overall accuracy. Figure 1 in the paper illustrates how different MLLMs perform across these metrics. For example, it shows that while some models might identify principles well, they struggle to apply them effectively in visual scenarios. Through extensive experiments, the authors tested various open-source and closed-source MLLMs on GeoSense. They found that Gemini 2.0 Pro Flash performed the best, achieving an overall score of 65.3 out of 100. This score reflects its ability to handle the benchmark's challenges, but even this leading model didn't reach human-like proficiency. The paper delves into why MLLMs fall short. Humans, as shown in Figure 2, solve geometry problems by first pinpointing relevant principles and then using them step by step. For instance, in a problem involving a circle and an inscribed triangle, a human might start by recognizing that the radii of a circle are equal, leading to an isosceles triangle, and then apply the triangle angle sum theorem to find the answer. In contrast, MLLMs often fail even when they perceive diagrams accurately or follow logical steps, because they don't reliably identify or apply the right geometric principles. The researchers provide examples from their analysis. In one case, as depicted in Figure 3, an MLLM might generate a reasoning process that looks plausible but misses key principles, leading to incorrect conclusions. This issue is highlighted in comparisons with benchmarks like MathVerse and MathFlow, which point out problems with visual perception, and WeMath, which touches on principles but doesn't fully assess their application in context. The paper's abstract emphasizes that this bottleneck, jointly in identification and application, hinders MLLM's overall reasoning abilities. By using GeoSense, the authors reveal that improving these areas is crucial for making MLLMs more robust and human-like in artificial intelligence. In the introduction, the authors discuss how GPS serves as a critical testbed for MLLMs, given the rapid rise of models like those from references cited in the paper. They categorize geometric principles as foundational elements, including definitions, theorems, and formulas, which are detailed in Section 2.1, though the paper excerpt doesn't go into that depth here. The experiments section likely includes more specifics, but from the provided content, we know they conducted in-depth tests across different subjects, as shown in the performance figures. For instance, subfigure A in Figure 1 covers GPI performance, B covers GPA, and C covers ACC, giving a clear breakdown of strengths and weaknesses. Overall, the findings from GeoSense underscore the need for future advancements in MLLMs. By open sourcing the code and dataset within a month, as mentioned, the authors aim to help the AI community build better models. This benchmark not only evaluates current capabilities but also paves the way for more sophisticated geometric reasoning in AI systems. The paper classifies under CCS concepts in the theory of computation, specifically computational geometry, and keywords include geometry problem solving, multimodal reasoning, and geometric principles. It's published on arXiv with the identifier 2504.12597v2 from April 24, 2025, and lists corresponding authors like Jun Song. In summary of the paper's contributions, GeoSense provides a systematic way to measure and improve MLLMs' handling of geometric tasks, revealing persistent challenges that could lead to breakthroughs in AI reasoning.